Okay, it is 8 a.m. Let's see. You have your third exam this coming Friday. It covers, I hope you know this already, covers the October 16th, the October 23rd, and the October 30th homework assignments. Okay, so it starts with finding absolute minima and maxima, and then there was intermediate value theorem, extreme value theorem, uh, mean value theorem, and we did all that curve sketching stuff. And then there were the optimization problems. And the last thing that will be covered on the exam is finding antiderivatives. Oh, I see Mr. Levy's face. How exciting. Okay.
Sorry, I was registering for my classes.
Okay. Okay, let's see. Yeah, still working on figuring out how to save my notes, but I think I'm making progress. Just piddle around with everything every day. Okay, any questions? All right, then let's talk about the fundamental theorem of calculus. Oh, remember to record. Let's, okay. Okay, so I'm sharing my screen. Thank you for that information. Okay. All right. Let's see. So, well, I got the date wrong. It's the second. The second. Correct that. All right, there. We started talking about the fundamental theorem of calculus on Friday. And what this theorem does is connect integrals and derivatives. Okay, basically integration and differentiation are inverse processes of each other. And the fundamental theorem tells you exactly how that works. Okay, so suppose you have a function that's continuous on the closed interval a, b. Then the fundamental theorem has two parts. We're going to talk about part one today. Okay, see what that means. Well, we talked about part two on Friday. Okay, part two, just to review a little bit, it says that the definite integral from a to b of little f of x dx is capital F of b minus capital F of a, where capital F is an antiderivative of little f. And okay, so f capital F prime of x is equal to little f of x. And notice that you put in two capital F, the endpoints of your integral, okay, a and b. So it's f of b minus f of a. A definite integral is a number. So let's use part two to evaluate a definite integral. Okay, here's an example. All right, so I want to evaluate the definite integral from 0 to 1 of 3 plus x times the square root of x. And let's see, I can use the properties of integrals to break that into the sum of two integrals. And also, while I'm at it, may as well write x times the square root of x in exponent form. It's x to the 3/2, right? Because you've got x to the first times x to the 1/2. For differentiating or integrating, you really need to write things like that in exponent form. Okay, so we need an antiderivative of 3. What's an antiderivative of 3?
Three X.
Okay, thank you. Okay, so 3x, and we put this vertical line to indicate we're going to evaluate 3x at 1 and at 0 and subtract. Okay, the top number goes in first, always. And what's an antiderivative of x to the 3 halves?
It would be X to the power of 5/2. All of that over 5/2.
Yes, thank you. Okay, and let's see. So I'm going to evaluate this one first. F of B minus F of A, that's going to be 3 times 1 minus 3 times 0. Okay. So I'm done with the first part. And then 1/5 halves I can write as 2/5. And so we've got 3 here. And let's evaluate this one. So now F of B minus F of A, 2/5. B is 1. And then put in 0. And 1/5 halves is 1. Ooh. Okay, I don't know where that came from, but whatever. That that red line, that was okay. It's gone. So it's 3 plus 2/5, which would be, well, you could leave it like that. 15/5 plus 2/5 is 17/5. Okay. That was what we were doing Friday. Does anybody have any questions about that? Well, that read things back. Okay. Well, let's talk about this first part. Let's write it down. If g of x then, okay, and then let's see, maybe put some, say something about what x is. X has to come out of your interval on which your function f is defined and continuous. Okay. Then g prime of x is equal to f of x for any x in that interval. All right. Well, this is a new way of defining a function. G of x the variable for g is x, and notice it's an endpoint for the interval. Okay. Bader, he's in my he's in my calculus 2 class. Okay, let me see if anybody else wants in here. Well, I'm going to let him in. I don't know why he want to come to the calculus 1, but whatever. All right.
Maybe it's because of the recent time change, and so he thinks.
Ah. Oh, that could be. Thank you. Yeah, in fact, I only have one meeting ID for Zoom. So if I have a Zoom meeting going on, anybody from either class can enter. And so can my friends if they want to. Okay, let me show you an example of this. Yeah, the variable for G as an endpoint for this definite integral. Okay, T represents well, all the numbers between A and X. So an endpoint, the letter used for an endpoint, you never want to use as a letter inside the integral. Because the inside letter, the T, is trying to tell you about what's happening for all the numbers between A and X. Here's an example of a function defined that way. L of x is the integral from 1 to x of 1 over t dt. And I'm going to allow x to be any positive number. Okay. So what's that function like? Well, I'm going to look at 1 over t dt. And let's see, maybe I'd like to have some lines and grids here. Okay. Coordinate system. And 1 over t looks like this. Well, it doesn't have that weird hump. Let's see if I can try that again. Okay. That's a little better. Okay, and let's call this one. So L of 1 would be the integral from 1 to 1 of 1 over t dt, which is basically given the area of that little vertical line segment. In fact, from the properties of integrals, we know that that's 0. If I look at L of, okay, call that 2, L of 2, well, that would be the integral from 1 to 2 of 1 over t dt. And, well, how can you interpret that integral? That would actually be giving me the area of this region right here. The yellow region. Okay. And if I take, well, let's call that 3. If I take L of 3, that would be the integral from 1 to 3 of 1 over t dt. That would be the yellow region plus, okay, I'll color it red. Still yellow. Mm, mm, mm. Let's see. Yeah. Now it's red. So this would be, okay. Now somebody wants in. This would be, oh, got to bring this. This would be the area of the yellow region and the red region put together. Okay, so yeah, we can for numbers that are larger than 1, we can interpret this function as giving you the area under the curve. In fact, you can also see, well, 0 is equal to L of 1, and that's less than L of 2, and that's less than L of 3, because L of 2, that corresponds to an area that's smaller than the area that corresponds to L of 3. In fact, for x greater than 1, 0 is less than L of x, and then take y to be greater than x is less than L of y. I'm going to get an increasing function. Because I'm taking areas, and the bigger x is, the bigger the area. What? Somebody got a question?
No, I think someone has their mic on.
Okay. Okay, so yeah, this is a perfectly nice way to define a function. And well, what does the theorem say? The theorem, you don't have to find any antiderivative here, okay? It says that the derivative of this function is basically that function. So okay, so let's let from 0 to x of this secant, never make that a different letter, secant of t dt. Secant does have an antiderivative, but we haven't talked about it yet. And I don't need an antiderivative of secant anyway. G prime is secant x. Okay. So let's practice some on that. Let me see. Let me get my book and get some examples here. So we want to find the derivatives. Okay, so how about the integral from 2 to x of the cosine of t squared dt, and that is my function. Okay. So I want to find f prime of x. So what's f prime of x equal to?
Is it
Somebody.
possible to use a chain rule for this one?
We're going to do some that need the chain rule, but this one doesn't. Okay. Look back up here. Look back up here. I've
Is
got,
it cosine x squared?
yeah. Oh, okay. Cosine of x squared. One thing yes, thank you for that. The number here, this number, it was 0 in the problem that we did first. It was 1 for this L of x. Okay. In this problem, it's 2. It doesn't matter what that number is. What does matter, you have to have your constant. Your constant has to be the lower number. Okay, so this number must be constant and your variable must be at the top. That must be the case before you can use part 1 of the fundamental theorem and conclude that f prime of x is indeed cosine of x squared. So basically, it's just this function in here, only you want your variable to be x now. And yeah, t, remember, t for in this definite integral, the t represents a number between 2 and x. Okay. Sometimes it's called a dummy variable. I think of it as the variable for the integral. Yeah, it's whatever this dt's the variable for the integral. Fundamental theorem says that that derivative is the cosine of x squared. Okay, but let's change it up a little bit. Suppose I ask you for, I'm going to call this g of x. G of x is the integral. That's supposed to be an integral sign. Okay. Let's see if I can do a better job. All right. All right. The integral from x to 2 of the cosine of t squared dt. Well, now the constant is at the top number and x is the bottom number. X is the variable for g, capital G. So when it's in this form, I can't use the fundamental theorem yet. But what can I do? Use the properties of integrals. Definite integral is equal to minus of the cosine of t squared dt. And now I've got it in the right form with a minus out front. Okay. Now the constant is at the bottom and the variable is at the top. So I can use the part 1 of the fundamental theorem to say that g prime of x is minus the cosine of x squared. Okay. Let's call so f prime of x. What is f prime of x for this function? Capital F of x is a definite integral from 0 to x of the square root of 1 plus 2t dt. So what's f prime of x equal to?
If not wrong, it would be equal to the square root of 2.
No. Okay. It's just 1 square root of 1 plus 2x. Okay. Yeah. Okay. This is so easy. It's almost hard. Okay. Fundamental theorem, part 1. You got this funny new way of defining a function. It's not so funny once you get used to it. Okay. So you got a function defined in terms of definite integrals. But for any function defined that way, the derivative is sitting right there for you. The derivative is just whatever is inside here with an x instead of a t. And this is true, okay? Actually, we could even prove this theorem. I don't know if y'all be interested in seeing that. But yeah, so it's just the square root of 1 plus 2t. But now, let's change it. So now, I'm going to call this g of x. What if I make that x squared? Well, now you need the chain rule. I know that, okay, because what is this really? We had f of this capital F of x defined above. And really, g of x, okay, so f of x squared, if I put x squared in the place of x here, that's by definition the integral from 0 to x squared of 1 plus 2t dt. So g of x is a composition of functions. And that means that, okay, g prime of x is going to be f prime applied to x squared times the derivative of x squared. And that means, okay, well, f prime of x I'll call it z. F prime of z is 1 plus 2z. So f prime of x squared is the square root of 1 plus 2 times, replace z by x squared. And that means that g prime of x is the square root of 1 plus 2x squared times 2x. Questions? Can you all still hear me?
Yes, ma'am.
Okay, good. Okay, let's do another one. H of x. Let's do it step by step, okay? H of x is the definite integral from 1 to x of the secant of t dt. In fact, we did this before, actually. Okay, so what's h prime of x?
Secant x.
Yes, it's the secant of x. Okay. Just that it's sitting right there in plain view. That's what part 1 says. All right, but let's make it more interesting. So I'm going to define a new function, g of x, now to be the integral from 1 to x to the 4th of the secant of t dt. And actually, well, it's not just x anymore, it's x to the 4th. So I stuck in a whole function, okay? And again, this is a composite. This is h of x to the 4th. Here's h up there. H of x to the 4th is the integral from 1 to x to the 4th of the secant of t dt. Well, I've got a composition of two functions here. I know that the derivative, just thinking about the fact that this is a composition, the derivative of h of x to the 4th. So inside function is x to the 4th, outside function h. By the chain rule, this is h prime applied to x to the 4th multiplied by the derivative of x to the 4th.
So is it secant x to the 4th times 4x?
4x cubed, almost, yes. Okay. So yeah, times 4x cubed. Okay, so g prime of x then would be, and okay, I didn't finish this. H prime was just secant of x. Okay, so h prime, if you put x to the 4th in, secant of x to the 4th, and I didn't leave enough room, times 4x cubed. So g prime of x, which is the derivative of h of x to the 4th, is the secant of x to the 4th. And I'm going to put that 4x cubed out front. Okay. So here we're using the chain rule. Okay. Here's another one. The integral from 2 to 1 over x, that's a 1, of the arctangent of t dt. Okay, well, x is the variable for capital F. And I guess x had better not be 0 here, because I'm taking 1 over x. But again, this is a composite, okay? Because if I define, let's see, let h of x equal to the integral from 2 to x arctan of t dt. And we want derivatives. Okay, we're looking for derivatives. Well, if I define h of x be, instead of putting that fancy 1 over x at the top, just plain old x, what's h prime of x?
It would be arc10 of x.
Yes. Good. Okay. That's the simple situation. Well, actually, my capital F of x is h of 1 over x. So composition now of h of, call it h of z. I call it, when we were talking about the chain rule, we always called it u. So why don't I call it that? H of u and 1 over x. Okay, we know that if we have a composition of two functions, f prime, the chain rule says that this is h prime applied to the inside function, which is u, times the derivative of the inside function. And that's h prime of 1 over x. The derivative of 1 over x, well, 1 over x is x to the minus 1. You could use the quotient rule if you wanted, but it's easier to write it as x to the minus 1 because then it's just minus x to the minus 2. And h prime was the arctan of x. Okay. So this would be arctangent of 1 over x times minus x to the minus 2. And I can write that as minus the arctangent of 1 over x squared. Okay, any questions? Does this look strange to you, what we're doing? Are y'all still there?
Yes, ma'am.
Okay.
And someone in the chat just said yes.
Okay. Well, it takes a little bit of getting used to. Okay. this is just a new way of defining a function, but it's something you can keep in your toolkit from now on. Let's think. Okay, let me get, here's a problem out of an old book. So let me see if I can graph this function. I'm just going to talk about this new way of defining this function a little bit. There's my coordinate system, and this is going to be t. And oh, I have this nice grid. Okay, so here's my graph, and it goes straight up, and then it comes straight down, and then it goes straight down, and then it's horizontal for a little bit. These are just line segments, and then it goes straight up. Okay, so this is 1, 2, 3, 4, 5, 6, 7, and this is 1, 2, 3, 4. Okay, and this is a graph. I'm going to call this function f. It's piecewise linear because it's composed of 1, 2, 3, 4, 5, 6 line segments. Okay. So I'm going to define capital F to be the integral from 0 to x of f of t dt. So f of 0 what's that equal to?
It will be equal to f of 0 times d0.
Well, okay, I guess you could think of that. Yeah, so it's 0, right? Remember that property of integrals? And in fact, it's also kind of the area of that little vertical line segment. We had this property of integrals that said the integral from a to a of f of x dx is 0. What's f of 1 equal to? There's one right there. Okay.
Is it 1?
No. Because, okay, f of 1 represents an area of a rectangle. Right? It would be the area of that rectangle. So what is it now?
Would it be 2?
2 in my picture. Okay. And what's f of 2 equal to? Well, you have to do a little thinking here. Let's see. That's okay. Let's see. So this, well, we already got f of 1, and we're going to just add that to. This is a trapezoid, right? And okay, this is a trapezoid. I could, okay, make it into a triangle and a rectangle. The area of this piece is 2. And the area of this triangle would be 1/2, base is 1, height is 2, it's 1. So that would have area 1. So f of 2 would be 2 plus 2 plus 1, because it's an area. It'd be the area of this rectangle plus the area of that rectangle plus the area of that triangle. So it's 5. Everybody see that?
Yes, ma'am.
And it is also this. Okay. And I could compute f of 3. Let's see, f of 3. Well, let's see, you got another triangle here, right? This is a straight line, so it's need the area of that triangle, which would be, okay, would be 1/2 base times height. Base is 1. The height would be 4, because that's a 4 right there. So that's 2. So the integral from 1 to 3 would be the sum of those areas. So it's 2 plus 2 plus 1 plus 2, which is 7.
Wouldn't the 1 on the integral be 0?
What?
On that last one you wrote down.
Yes,
No,
yes,
what?
sir. Yes, it would. Thank you. Thank you. I could actually get, well, like the integral from 2 to 3 of little f2. But yeah, okay. We're focusing on defining a function like this. So far, we're just, well, the little f is above the x-axis. So the definite integral is going to correspond to an area of a region, okay? Well, what happens when you go to 4? And that's supposed to go through that line, actually. When we go to 4, now the graph is beneath the x-axis. So let's see. So now we've gone beneath the x-axis. And if I want f of 4, well, it's going to be the sum of all this stuff I already computed, plus, so it's going to be 7. Right, it is just 2 plus 2 plus 1 plus 2. And then I'm going to get negative whatever the area of this little triangle is, okay? Well, that little triangle has area 1/2, I believe. Yeah. Base, height, base is 1, height's 1. 1/2 AB would be 1/2. Okay, but I subtract it because now the function is, well, essentially the height is -1 instead of +1. So this would be 7 minus 1/2, which would be 6.5, which would be 13/2. And f of 5. Well, it would be what we just got plus the integral from 4 to 5 of f of t dt, because I can break up, again, properties of integrals, I'm allowed to break up integrals to the sum of 2, right? Break the region up. So this is the integral from 0 to 4 of f of t dt plus the integral from 4 to 5 of f of t dt. And we already computed that, so we just need to compute that. Again, that's going to correspond to another, oh, let's see. Well, actually, if I just did this as a whole, then I'd have a triangle and I wouldn't have to worry about a trapezoid. Okay. So how about I break it up differently? Break it up to the 0 to 3. And then 3 to 5. I can also do that. 3 to 5. So that would be 3 to 5, and then 7. Okay, because that's where I was at 3. So this would be 7 plus, and then this integral would be negative the area of this green triangle. So 3 to 5, that's got base 2, height 2, well, actually negative 2, which would be a minus 2. So this would be 5. And, well, I could go on. Okay. The next time you'd add on a negative 2, and then you'd add on negative the area of that for the 7, that triangle. But okay, this is one where you can actually compute capital F of X from just looking at the graph. And yeah, so that's a new way of defining a function. And there are a lot of functions. This is one. This function has a name. Okay, I forget what it's called. But yeah, sine of t squared. Oh, it's almost time for us to go. Sine of t squared has an antiderivative because it's a perfectly nice function. It's continuous over all the reals, but you can't write it down in elementary terms. So you have to give it a name, okay? And maybe this is CSGN of X or something like that. But people need to integrate things like this on occasion, so they just give the function a name, and then it becomes part of your usable tools in your tool bag. Well, we are pretty much out of time, so we'll call it a day, and you can go if you, please, class is over. If you want to hang around and ask a question or two, that would be great too.